All right, guys. So what we're going to be talking about today is essentially, we were talking about the instantaneous rate of change last time. So you said the limit as h approaches 0 of f of a plus h minus f of a all over h. It's also called the derivative of f of x. This is called the derivative of f of x at x equals a. Okay? And we denote that by f prime of a. It's another way to write derivative. F prime of a. And that's kind of not the best penmanship, but if I would write that again for you. F prime of a, essentially. It's another way to write derivative. And that being said, it's the slope of the tangent line. The slope of the tangent line. Okay? At x equals a. It's the tangent line touches f of x at x equals a. So it's exactly at one point, essentially. So you have, that's the tangent line, exactly at that point, let's say. So f prime of a would be the slope at a. So f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. This is also known as the definition of the derivative. That's what that is if you've seen that in your textbook. F prime of x can also be written as d dx. That means the derivative with respect to x of that function, f of x. So if you have like f of x plus x, then if you do the limit as h approaches 0 of f of x plus h minus f of x all over h, right? Here you get 1. What's going to happen is that x plus h minus x would be h over h is 1. Meaning that the slope is going to be 1. Okay? What if you had x squared, like a parabola, using the definition of derivative? So f of x equals x squared. So f prime of x equals limit as h approaches 0 f of x plus h minus f of x all over h. Okay? So limit as h approaches 0 of x plus h squared all over h minus x squared. X squared, yes. What happens is that if you expand that, you get the limit again as h approaches 0, square the first term. So these cancel. And that's still all over h. So you have limit as h approaches 0 of 2xh plus h all over h. So if you factor out the h, you get 2x plus h. And if you put in 0 for h, you get 2x as your answer. So that's the derivative. What about x cubed? Same idea, right? If you did all that, you get the fact. We can kind of run through it. We're not going to do it all in depth. That's a lot of time there. F prime of x, it's an x by the way, equals a limit as h approaches 0, x plus h cubed minus x cubed all over h. So you can square it first and multiply it again. But you're essentially going to end up with something like this as you continue. And that's the golden part where the h's cancel. And anything else with an h, because you'll write this line down. Anything with an h, when you sub in an h, when you evaluate the limit, it's going to go away. You're going to be left with 3x squared. That will be the derivative of x cubed, essentially. You can also do the same thing with square roots. So you have right here f prime of x limit as h approaches 0 of root x plus h minus x, root x, all over h. What you're going to do is you're multiply by the conjugate, it's called. We're going to multiply top and bottom of this by root x plus h plus root x all over h. Actually, you're going to do the same thing on the bottom part of it. So you're going to do root x plus h plus root x. So we're going to get limit as h approaches 0 of x plus h minus x all over h, root x plus h plus root x. Because these would go and get x plus h, this would cancel with negative version, that'd be negative x. These two x's would cancel, so you get limit at h approaches 0 of h over h of root x plus h plus root x. These h's cancel as well. And you get limit so when you sub in 0, you get 1 over 2 root x. That's your answer. Okay. So in terms of right now, if you had to find equate the tangent using the definition of derivative to get full marks. Of x squared plus 2x plus 3 add x equals 2. We would do the definition of derivative. Okay? So you go, really what you can do, I guess you can sub in f prime of 2. Prime of 2 equals limit as h approaches 0. 0 right there, and that's an approach sign. 2 plus h squared plus 2 times 2 plus h plus 3 minus the function actually evaluating at 2, which would give you something along the lines as 4 plus 3, so it's plus 11 all over h. So essentially, if you were to simplify all this, like you'd square this, you'd FOIL all this, you'd get limit as h approaches 0 of h plus 6 all over h. These h's would cancel, and you get limit as h approaches 0 of h plus 6. If I put in 0 for h, I would get that my answer is 6. So that has to be the slope at 2 exactly. So what would happen now is, now that I know that y equals mx plus b, and I don't know what the value of it at 2 is, but I can go f at 2, the function itself at 2 would give me 2 squared 11, right? So if I were to solve this for the b, I put the 11 for the y, the 6 that I found, the 2 plus b. So I would get something along the lines of 2 squared is 4 times 4. 4 plus 4 is 8, 11. 6 times 6 is 12. Let's try and see what they did here. So yeah, you get b equals some other value, which is 11 minus 12 equals b, so b equals -1. So the whole equation would be y equals 6x minus 1. That would be your actual equation of the tangent line using the definition of the derivative. The thing is, when we do like an absolute value, if you were to actually solve it, you'd get into a pretty hairy situation. Because the limit does not exist. So if you had f of x equals the absolute value of x at x equals 0, what happens is that you go limit as h approaches 0 of 0 plus h minus absolute value of 0, or h, equals limit as h approaches 0 of absolute value of h over h. Problem with this is that based on our previous unit, this limit doesn't exist. Yeah, there's no slope. The absolute value. That's what really sums it up right there.